Hello everyone, my name is Christine Park and this is Lab 2, which deals with drag force. So just to give a brief introduction about this lab, the objective was to observe an object that was moving straight down in a straight line. I recorded this footage and created an experimental model using the tracker software, and then two computer-generated models, one accounting for just the force of gravity and then another that accounted for gravity as well as drag force. The main physics principle that was addressed in this lab is Newton's second law, or the momentum principle, which can be expressed by acceleration is equal to net force over the mass. From this, we have a basic understanding that acceleration is dependent on the net force, and in this specific situation, we can visually assume that the object is accelerating downwards as it is being dropped, so we know that there are forces acting upon the paper ball. In this lab, we are trying to find out what that force is. As we already have the force of gravity, we are trying to find the force that's moving in the opposite direction, which is drag force. So here's my experimental model of me dropping the ball, and from this model, I was able to extract a few key points of data. Firstly, being the start time, which was 0, the diameter, which was relatively 0.036 meters, the starting velocity, which was 0, and the observed end time, which was 0.502 seconds. From there, I was able to move on to the computational model, which just focused on the gravitational force without accounting for drag force. So in the code, I modified the mass, which I modified to equal 0.0029, G, which would be the force of gravity, which is 9.8, W, which is the weight force, which is the mass times gravity times the unit vector. In this case, if we're just focusing on gravity, the net force would just be equal to W. I set the velocity of the ball to ball dot velocity plus the net force over the mass times the change in time, and the position of the ball to ball dot position plus ball dot velocity times change in time. And these are my results. So then I graphed both sets of data onto a line graph to kind of see where they were at this stage. As you can see, the experimental data did not travel as far down in the y direction as the model predicted data had suggested, and this indicates that there is another force acting on the experimental model. So the next step for me was to start creating a computational model that accounted for gravity as well as drag force. So to do this, I focused on modifying one section of the code, which was the net force. Previously, net force was just equal to W, or the weight force, but in this case we know that there is another force we have to account for, which is drag force. And then we also have a basic understanding that the drag force is proportional to the square of the speed of the object. So to do this, I added a line which stated that FD was equal to B times the unit vector times the magnitude of the ball's velocity squared. And these are my results. So from there, I graphed all three data sets onto a line graph and was able to find certain findings. So in the blue, you can see the experimental data. In red, you can see the model without drag and just using gravity. And then thirdly, in yellow, you can see the graph data of the ball, of the graphed computational model that accounted for gravity as well as drag force. You can see that the experimental data is still different. It still does not travel as far as the experimental and as the computer models had suggested. And there are various reasons that can explain this. Firstly, being that the object, when it was dropped an off ball in a completely straight line, which could have visually altered the data. Secondly, there could be a sense of human error when it came to accurately locating the point mass in the center of the paper ball between each frame and tracker. And then thirdly, the crumble ball had a very irregular surface with different exposed surface and irregularities, which could have contributed to it catching on different pockets of air, which could have affected how it traveled. And then to answer the what does it mean questions. So when you're examining the velocity versus time predicted by the models with and without drag, which models, if any, predict the terminal velocity? So the answer to this would be that the model that model drag force as well as gravity would represent terminal velocity, because terminal velocity is determined by the velocity that is reached when the drag force and the force of gravity are equal to each other. The next question. So if the object was initially thrown down rather than just dropped, would the terminal velocities be the same or would they be different? So for the visual answer to this question, they would be the same. So in the computer model that I created, I just set the initial velocity to 1 in the y direction rather than 0. And you can see that towards the end, these slopes end up becoming the same. In other words, the lines become parallel, which indicates that the velocities are the same, that they are constant. This can also be explained by the formula, which is drag force is equal to 1/2 CPAV squared. So as the paper's velocity increases, the magnitude of the drag force increases until the magnitude of the drag force is equal to the gravitational force, which yields a net force of 0, which means there is no acceleration, which is shown by Newton's second law.